Alright, welcome back guys. We're going to be covering section 8.2. So we're just going to be investigating more about the behavior of polynomials. Okay, so in 8.1 we talked about the zeros, or the last thing, were the zeros of the polynomial. And we've talked about that before. They're just values of x such that they give you outputs of 0, okay, from the function. But we also saw that those zeros can have multiplicities, okay, or in a sense they can be repeated. And so now we're going to look at some other characteristics of these polynomials. And the first one, I'll read this one here. So let's say p of x, or f of x, whatever you want to call it, is a polynomial, and it is of degree n. Okay, so n is just a number, so it could be a second degree or quadratic. It could be a first degree, a linear, it could be a cubic, a fourth degree, fifth degree, etc. Then we can know these two properties about it. It will have at most n real zeros, okay? And consequently, it'll have at most n x-intercepts, because remember, the zeros are related to the x-intercepts, right? The 0 is the value of x, and then the x-intercept is the actual point on the x-axis with that value of x, where the function either touches or crosses. Remember that, depending on the multiplicity of the 0. So let's think about this. This means that a quadratic function can have at most 2 real zeros. A cubic function could have at most 3. A fourth degree polynomial would have at most 4. Now this does not say it has to have that many, but it can't have any more than that number. Okay? And also remember, because we saw some examples of those quadratic functions in which some of the zeros were not real. They were not real numbers, were they? They were imaginary or complex. They had an imaginary component. And then the second bullet point says a polynomial of n degree can have at most n minus 1 turning points. So think about this. Our basic quadratic function, x squared, any sort of quadratic function is always a parabola, right? Depending on the orientation of it. Well, how many turning points does a parabola have? It just has 1, because it has either a maximum or a minimum. And if it's a quadratic function, the degree is 2, and 2 minus 1 is 1, so it can have at most 1 turning point. And in fact, we see that. A cubic function is of degree 3, so it could have at most 3 minus 1 or 2 turning points. And we've seen that with cubic functions before. A lot of them go up, they turn, they come back down, they turn again, and then go back up, right? They may have both a relative minimum and a maximum. All right. And then here I just tell you that a turning point, remember, is basically where you're going to have either a relative minimum or maximum, or where the function changes from decreasing to increasing or vice versa. All right, so let's look at example 1 here. And then just remember, the degree of the polynomial is the highest exponent. Okay, we covered that in 8.1. So if we know the degree, we can know the maximum number of zeros, and also the maximum number of turning points that the function would have if we were to graph it. Okay, so let's look at example 1 here. For this particular function, we want to state the maximum number of real zeros, the maximum number of x-intercepts. Well, this will be the same as the maximum number of real zeros, and then the maximum number of turning points that the graph of the function could have. So let's look at this function. Let me zoom in. It is an 8th degree polynomial. Okay, so I'm going to put up here that n is equal to 8. And so if it's an 8th degree polynomial, then it can have up to 8 real zeros. And because the real zeros, or the zeros, are just the x-coordinates of your x-intercepts, it can also have up to 8 x-intercepts. Now, a lot of these polynomials, guys, they're not going to have that maximum. Okay, this one might only have 4 actual real zeros. And then part C, the maximum number of turning points is just going to be 1 less. Okay, n minus 1. So in other words, 8 minus 1, which is 7. So that means the graph of this function could have at most 7 turning points. And again, you know, it may or may not. We could graph it real quick in Desmos. Let's see. X to the 8th minus 4x to the 7th. Let's see. Plus 3x minus 4. Okay. Well, I'm not sure why we're getting this down here at the bottom of the screen, but you can notice, as far as I can see, at least right in this region on the x-axis, there's just 2 real zeros. See that? You know, over here on the left-hand side, as x goes to negative infinity, I don't know if this function actually turns around and then goes back up or not. But my guess would be it maybe only has 2 real zeros. And you can see it only has, well, it looks like it would have 3 turning points, right? This is a turning point, this is a turning point, and down here, evidently somewhere, if we keep zooming out, it's going to have another turning point down there, at least as far as we can tell. Okay. Desmos is looking kind of weird. Maybe I need to reload this screen before we look at another one. But anyway, another indication here, guys, as to whether or not this might have other zeros that we just can't see further out on the x-axis is to kind of look at the end behavior. Because the leading term is x to the 8th, that tells me, if you remember from 8.1, that both ends will be going up. And so that's what I see already, okay? So if both ends aren't going, or for that, we could potentially have some other zeros way out here, but the ends are going to have to come back down and then go back up again, okay? So, like I said, that leading term, knowing what that leading term is pretty powerful in getting an idea of what the graph of a function is going to look like. I'm going to refresh this or reload it. There we go. Alright, so let's get back to the notes. Yeah, and this is what I was just mentioning. So remember that the leading term and the degree of the function will dictate the end behavior. Now, there's another piece of information we can know fairly easily, and that is the y-intercept. The y, and typically in my classes I'll ask, is every polynomial going to have a y-intercept? Or in other words, is every polynomial going to cross the y-axis? And the answer is yes. The reason it's yes is because polynomials are continuous. Because remember, their domains are all real numbers. So for a polynomial to cross the x-intercept, or I'm saying this backwards. Let's look at Desmos here real quick. For a polynomial to cross the y-axis, any point on the y-axis would have an x-coordinate of 0. Well, 0 is in the domain of any polynomial function. Okay, so every polynomial will have a y-intercept. Now, how do we find it? Well, it goes back to what I just mentioned. For it to have a y-intercept, it has to cross the y-axis, so there will be a point on the y-axis. Well, what's the x-coordinate of any point on the y-axis? Well, its x-coordinate has to be 0. Okay. So to find the y-intercept, or to find that y-coordinate of that point, you just plug 0 into the function. Okay, or in other words, you evaluate the function whenever x is 0. And just as I've written here, your y-intercept is going to have this form. Okay. Now, don't confuse this with your x-intercepts. They have this form, right? Because for a point to be on the x-axis, the y-coordinate has to be 0. All right. So lots of times you can determine where the y-intercept is going to be just by inspecting the function. So look at this function here. If I were to plug 0 in for those x's, these first three terms would disappear and I'd just be left with -4. Now I don't have that function still up, or we'd look at it, but it will cross the x or the y-axis at -4. Oops. Alright, well, let's look at an example 2 here. It says for this particular function, and this is a polynomial, it's a 5th degree polynomial. It says use the leading term test and knowledge of the y-intercept to match the function with one of the graphs below. Okay, so it's going to be one of these. Well, let's first think about the end behavior. Okay. Well, that hinges upon the leading term, right? The leading term is x to the 5th. So the leading term is x to the 5th, which means the leading coefficient is an understood 1, which is positive, and then the degree is 5, which is an odd number. Okay, so you may have to go back and look in your notes. But if the leading coefficient is positive and the degree of the polynomial is odd, then the end behavior looks like this. The left tail is going down and the right tail is going up. Okay. And so really, guys, with just that information, we could pick out the answer to this question. It's got to be F. F is the only one that has the appropriate end behavior. Now we could figure out the y-intercept. The y-intercept would be equal to, or it would be the point where x is 0, and then to find that y coordinate, you just plug 0 into your function. And if you do that, again by inspection, all of these terms with x's go to 0, and you're just left with 4. Okay, so whenever x is 0, y is 4. So your y-intercept is this point, 0, 4. Or in other words, our function is going to cross the y-axis at 4. That's actually what we see with this function right here. Okay, so the answer to number 2 is F. Example 3 references the same group of functions. It says for this polynomial, use the leading term test and the y-intercept to match the function with one of the graphs. Okay, so we're going to do it the same way. Alright, well, these polynomials, they are written in standard form or in descending order. That just means that the exponents are decreasing. So the leading term is the first one. Okay. Alright, so the leading coefficient then will be that negative 0.5. Okay, so in other words, the leading coefficient is a negative number. And then the degree of the function is 6, which is an even number. Okay. So for the end behavior, it goes back to the leading term test. If you look back at your chart, the degree is even, so both tails will be doing the same thing. The leading coefficient is negative, which means both tails are going to be going down. Okay. And then as far as the y-intercept goes, the x-coordinate will be 0, and let's see what that y-coordinate is going to be if we plug 0 into this function. Well, all of these variable terms will turn to 0, and we'll just be left with negative 3. Okay. So this function, both tails or both ends will be going downward, and it will be crossing the x-axis at negative 3. So let's see which of these. Well, there's only one choice in which both tails are going down, and it's choice A. And you may say, well, how can we tell if it's crossing at negative 3? Well, it's hard to tell because the y-axis here, in order to actually see all of this graph, the y-axis has been condensed a lot. In fact, you can see that each increment is an increment of 100. Okay, so if it is in fact crossing the y-axis at negative 3, it should look like it's real close to the origin, and it in fact does. Okay, so this one's going to be choice A. And then again, you can graph these in your calculator or using Desmos if you need to. Alright. So I think I'm going to do a part 2 video because I don't think I'll have enough time. We've got 2 examples left. But what we want to do is we want to look at how to graph these by hand. Okay, that will involve determining the end behavior, determining the y-intercept, but also determining the zeros or the x-intercepts. In other words, where's the function touch or cross the x-axis. And with that information, we can roughly sketch the graph of a function. Okay, so I think I'm going to save that for the part 2 video.